want to take a look at a lotto ticket and some of the things we have, and then we'll get into this concept of at least once. Since a probability is a fraction of good, right, or success over total, we can look at the lottery ticket this way, where you must buy a ticket, you got to pick 6 numbers from 1 to 40, and they can show up in any order. But our lottery that we're making up is very similar to the first lotto that they had in Connecticut years ago. It requires picking 6 numbers from 1 to 40. And you have to get all 6 to win the jackpot. But if you know the lotto, it doesn't matter what order they come up in. So you're not looking for a permutation, you're looking for a combination here, where the set of 6 numbers that you pick is the right set to match the ones that come up when they draw them out of a barrel with 40 balls in them. So the probability of winning is how many winning combinations are there. So if you take the combination, as they do when they put them in the newspaper or online, and you put them in numerical order so they're easier to check, then every ticket is in numerical order also. It almost looks like you hit the permutation. That's because the results and the tickets are all printed in numerical order, not based on the order they show up in. There's only one winning combination, but there's a lot of combinations, literally combinations. I'm not just using it colloquially. Combinations are sets of where we can get those numbers, and what that would be is there were 40 that we're drawing from, and we're doing a combination of 6. And therefore what we have here is we're going to find the probability of winning this lottery. So it's going to be 1 over, and 40 choose 6. So we're going to go 40 choose 6 will be, right, it's going to be underneath the 1. We have our 40 factorial. Over now it is a combination. So besides taking off 40 minus 6 for 34 factorial, we also have the 6 factorial. So why don't we invert it, right? Well, let's just keep it the way it is actually. 1 over, keep it the way we're working on it. And we'll go 40, 39, 38, 37, 36, 35, and then 34 factorial. And then over here we'll take the 34 factorial. We also have our 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. So we'll take out the 34 factorials, ones each. And we'll start knocking out, right? Maybe in this case we'll say, where can we get rid of 3 times 2 divided by, this becomes 1 and this becomes 6, and we'll divide that 6 out, and 36 is gone. And let's take this, divide by 5, get 1, divide by 5, get 8, divide by 4, get 1, divide by 4, get 2. What we have now is we got a 1 on top, and we don't have to worry about all these ones in the denominator of the fraction down here, but we have 2 times 39 times 38 times 37, 36 is gone to 1, times 35 equals. So that's what it worked out to. And there are shorter ways, and I'll go through that to help you stay fresh on how to use this kind of calculator and other options. But what we have here, when I clear it all out, is 1 divided by, and I'll put parentheses around, 2 times 39 times 38 times 37 times 35. And I'll close it, and I'll see what we get. And apparently this guy's thought is to call it 2.605265763 e negative 7, which means it's like 2.6, we won't go beyond that by our choice right here, times 10 to the negative 7, which means that it's 2.6 if it was 10 to the 0. But we need it to be a much smaller number. This changes orders of magnitude. The 2 and the 6 are going to be digits in what we have. But what we have to do is not take this and make it like 26 and bigger. We have to take this and make it smaller. So we're beginning here. 1, 2, 3, 4, 5, 6, 7 times. We have our decimal point. Okay. 1, 2, 3, 4, 5, 6. So point 1, 2, 3, 4, 5, 6, and then 2, 6. That's the probability of having the winning ticket, even though they could come up in any order. I mean, we're thankful for that because this one right here meant that we don't have to get them in the right order, and that made us more likely to win. So yeah, the odds or the probability of you winning, even in this one where there were only 40 numbers and you only had to get 6, you don't have to pay extra for Powerball, you know, an extra $1 to qualify for the big jackpot, and you don't have to pick an extra number on the side that they draw out of 40 others or whatever it is. With the red ball, the Powerball, that makes it even that much, with an extra multiplier, harder to win. But the odds or probability of you winning a lottery like this are, let's just say, not very good. There are some prizes that are for less. I know that one time I hit 4 numbers. I think it paid, am I remembering this right? Because I got the ticket for my birthday, and it hit 4, and it paid like $45, something like that. My Aunt Mary was in her 80s when she hit 5. Why she was playing lotto in her 80s, I don't know, but she hit 5 of them, and here's what she said. They really made me mad. They made you mad. She won like $4,000 in the lottery, went and cashed it, and they gave her the $4,000, and then at the end of the year she had to pay taxes on that, and she didn't have them withhold the money, which she could have done. But when someone said, do you want us to keep some of your money or do you want it all, of course she said, I'll have it all. And then when it came time to pay her taxes the next year, she owed a significant portion, like $1,000 more on her taxes from having won the lottery. But I said, you know what, I'll just remove the whole thing from the problem. I didn't actually say it, but take the problem off your hands. Give me all the money, I'll pay the taxes when they come due. There are other stories I could tell you, but we don't have time for that, about how the tax problems go like that with winning big prizes. But not a good chance of winning here. Now, I want to take that into at least once. So this was drawing back on our concept of probability and on combinations and getting some perspective on those lottery drawings for things like Lotto or Powerball. Now what we had done was we had done 1 over 4 choose 6. So if I clear this out and I go with 1 over, and then I do math and I go to my probability, nope, I did it wrong. I want to go 1 over, and then I want to go put in my 40, then I want to go to math, go to my probability, find the NCR because it's a combination, 6, and then tell it, you know, go ahead and calculate that. It gets that 2.6052 times 10 to the negative 7th. And there's a median way you can do that with factorials on your calculator. So several ways. I want to define, it's going to sound a little weird, but having a definition like this helps you understand where it comes from and how we're going to work with it. At least once, as a phrase, means, okay, ready for it, it is false that this happened 0 times. Now I know no one seems to talk that way, I get it. But it's helpful when you're doing things like this or dealing with logic to put it into a standard way to say, if it's at least once, then the only thing it's saying is it didn't happen 0 times. Okay, it could be something that's difficult to have happen, but to have it happen at least once means of all the times you tried, it didn't fail to happen every single time by happening at least once. So it's false that it happened 0 times. I always like to refer to the statement when someone says the phrase and you take it literally as what they're saying, probably not what they're meaning. If someone says to you in whatever context, I ain't got no money, okay? That means it is false that I have no money. So what does that mean? If you take them at what they've said with the words, not with what they mean, which they expect you to understand, they're saying it is false that I have zero money. So they have some money. But they're actually trying to get the point across in most cases that they have no money. It is true that I have no money. That's true, they have no money. Or it is false that I have any money. Would both be saying I have zero in terms of my money count. But that's the case of a double negative. We want to look at this one. And I want to look at it that the probability of anything is of A happening at least once equals 1 minus the probability that A happened 0 times. Therefore, if you try something a million times and you want to know the chances that it happened at least once, if you can find the probability that it didn't happen at all, subtract that from 1, which represents 100% of the possibilities, you'll see what's left over, and that gives you all combined together the ones that had at least once, but that could be twice, 3 times, or even more than that. Okay, a lottery ticket. This is probably an instant lottery ticket. Has probability of winning something of 0.3. How much? Do you win the jackpot? Probably not. Do you win, you bought the ticket for $1. Do you win $2? Many of the winners are $2. Do you win $1? Or do you even have one that says you win another ticket? And I quickly tell you that when I do get these tickets and I win $1, sometimes I'll take them back to the store and cash it in for $1, and they'll say, do you want $1 or do you want another ticket? The reason they want to sell you another ticket is they make profit every time they sell you a lottery ticket. If they give you the $1 back, they don't lose the money, they do get that back from the state, but they don't make any money on the transaction. But if you were to sell them the ticket, let's say they make 5 cents on every $1's worth of lottery tickets that they sell, well then, by me saying, oh, I'll take the ticket, they're making 5 cents on the transaction instead of making 0. But I always take the money because the expected value of these lottery tickets is almost always negative. So if I can convert something that says it's worth $1 to $1, I would rather get that than a ticket that's worth, I don't know, between 50 and 87 cents based on its expected value. But they always make a weird face because it's like, he's like the only guy that takes $1 back. But I do. So I want to look at, if that's the probability of a lottery ticket winning, 0.3, find the probability of winning at least once when you buy 5 tickets. I'll let you think about it, catch up, whatever that is. And also I do this in class every time. I talk about the first time Connecticut sold its first 10 instant lottery tickets. I still remember them to this day. They had a nice black, silver, and red ticket, and you scratched off 6 places, and if they had 3 that matched, you won that amount. The first 10 tickets were sold to Governor Ella Grasso at the time. She took the 10 tickets and she scratched them, and she didn't win any. And the camera was on her, and she said, I'm never doing this again. What a terrible campaign that was. All right, they show her losing, and she's saying, I'm never going to do this. This is a terrible idea, so that doesn't sell the tickets. Well, you know what would have been worse? If she won the jackpot. Imagine she scratches a random ticket and wins the jackpot as the governor. That would have probably been even worse. They've been doing okay with the lottery since then, but that wasn't thought through. But there was a chance that she should win something if she bought 10 tickets, and there's a 0.3 chance of winning. If you even look at what's the expected number of tickets that are winners, it would actually be 0.3 times 10. She'd expect to have 3 winning tickets on average there, and she got 0. So we'll take a look at something very similar. This is a person who only bought 5 tickets. So let's find the probability of one ticket does not win. We'll call that a loser. Okay. You know the probability of winning with one ticket is 0.3, so you take your 1 minus 0.3 and you get 0.7. That's the probability of an individual ticket losing. So now we want to find the probability that there's at least one winner. So if you have one ticket losing at 0.7, what's the probability of 5 losers? Well, the probability of the first one losing is 0.7. Probability of the second is 0.7. There's only 5 of them, so I'll write them out for you, but you may recognize that you might prefer to write that as 0.7 to the 5th power. Right, so back to the beginning, 0.3 chance of a ticket winning, 0.7 of an individual ticket losing. Tickets are considered to be independent events, so we get to multiply their probabilities together. So the probability of having all the tickets lose is when we take this 0.7 and we power it up to 5. 0.16807. That's the probability that you actually had 0 winners. So the probability at least one winner in 5 tickets is 1 minus that. And that's going to get you 0.83193. 83% chance that you would do that. That you would win at least one. Let's find out, same kind of numbers were there when Ella Grasso bought those 10 tickets. So let's do the 0.7 for her thing and find out how unlucky she actually was. 0.7, we'll power her up to the 10th power because she bought 10 tickets. And then we'll subtract that from 1. 97% of the time she would have won at least one. She found the 3% in probability that she wouldn't even have any winners among them. They were just hoping for some winner that was a small amount and showed simulation. She spent $10, maybe she won 2. It didn't work out. But that's how we will deal with at least one. So I like to do this with the dice too, though. No lie, a couple semesters ago, I did this 3 times in a row, and then I was like, you know what, I'm just going to stop, because what we're going to do is we're going to find a probability. We're going to roll dice. Let's go with the 5s. What's the probability of rolling at least 1 5 and 6 rolls of a fair die? Now I say 6 because that's a good choice for this reason. We'll take 6 dice and roll them all at the same time. It's essentially the same as rolling a die 6 times in a row. But we're going to write that up before we get going here. Now I'll roll them against the wall and we'll see what we get. But the reason I'm rolling 6 dice is because that works out with the law of large numbers to the idea of each one should happen once. I don't expect that to happen. It could, but even that is unlikely. But the idea here is you expect one of them as an expected value. If you roll it 6 times, you expect one of them to be 5. So I'll write that up here for us first. How many 5s are expected when we roll 6 dice? The answer is the expected value. 1 out of 6 will be a 5 times 6 that we get, and we expect to get 1. And that'll be useful when you're doing the dice quiz lab at home, trying to figure that one out, that you have to roll that and come up with the expectation, watch it against the law of large numbers and so forth. But the question is, find the probability of at least 1 5. rolling 6 dice. Probability of rolling a 5, 1 out of 6. Probability rolling 1 die, not a 5, 1 minus 1/6, 5 over 6. Probability no 5s in 6 rolls. So you take that 5 over 6 and you power it to 5. Let's get that number. 3 decimal digits will be enough to give us a good idea of what's going on. So we take 5 over 6 and I hit equals. And then I power that to the 6th. 0.335. Therefore, the probability of at least 1 5 in 6 rolls is, take the 1 minus the 0.335, and you're looking at this thing being 0.665. About 2/3 of the time, you'll get at least 1. Now what happened is I did that 3 times in a row and then we stopped one year because I seen if we got any 5s. Nope, no 5s. Nope, and I had people looking and all that. So let's see. The expectation on average is we'll get 1 5 out of all 6 dice. The likelihood that we'll get at least 1 is 2/3 of the time. And of course, that year I could have said something other than a 5 and that would have been different, but for whatever reason I've been doing 5s for a while and I'll stay with 5s. So here we go. The probability of getting at least 1 5 is about 2 3. 3 1 1 4 2 5. Okay. So what happened there is I got a 1 2 3 4 a 5 and an extra 1. I didn't get a 6. But actually that came out pretty close to expectation. So what happens is I do it 3 times for this reason. That one had a 5. We should expect, if the law of large numbers decides to play nice with us for a very short roll, that one time we're going to get no 5s and the other 2 times we're going to get at least 1 5. So there's one roll where we did get at least 1 5. Here's the second roll. And I read you 4 6 2 5 5 6. That also had 5s. It had multiple 5s, no big deal, but well, that's 2. Now, if the law of large numbers was a rule we could always rely on to happen in very short runs, oh, that's twice in a row that it happened, and 2 times out of 3 it's supposed to happen, so then people would think, I guarantee that no 5s are coming this time. And that's what's wrong with the law of large numbers, is it doesn't work in small batches. It only works, the larger the numbers, the better it goes. So don't bet a whole bunch of money on this saying, I know that it's due, because that's crazy. Let's see what does happen. 5 6 4 5 5 1. The 5s are coming out like crazy. So anyway, each time we got 5s. And I'm not here to roll the dice and show you that there's a perfect way to know exactly what's coming out, but it's mildly unusual that it happened all the time. So now if you do it 100 times, or let's say 120 times, it should come out very close to the average of having 80 times when a 5 showed up at least once and 40 times when it didn't. And that's what the law of large numbers, which we had in lecture 5, is saying. But this concept of at least once is it's been working with something we call the complement. The complement is everything but, right? So at least once is the complement of having 0 occurrences. And so we saw that at hard work here, because when we did this idea with probability of rolling 5 with 1 die, 1 out of 6, the complement of that is 5 out of 6, then it's not a 5 when you roll 1 die. Then we took the independence of the rolls to have, I put a 5 here, but I know it's a 6 that I'm supposed to have there, so let me fix that in purple. Because we did roll 6 dice. And I like using this number because it comes up with, 2/3 of the time you should get a 5 at least once. So standard use of likelihood of not getting a 5. Independent events lets me multiply 5 over 6 times 5 over 6 till all 6 of them are present. Subtracting that from 1 tells me the likelihood that we get at least 1. And that's what's going on as we're looking at the work that comes when we do at least 1. So I want to work on the 100-year flood problem. It doesn't rain for 100 years. A 100-year flood is a flood that's so bad it's only supposed to happen every 100 years. Now, the definition of the 100-year flood has been changing lately because there are some people that believe that the environment is changing as well, and that things that are supposed to happen every 100 years are happening more frequently. Okay, hurricanes, floods, some say wildfires, right? These might be related to, if there are changes in the climate, what's going on in the frequency of them. Others say no. So I leave it to you to decide what you want to do with that. But let's look at the 100-year flood as defined, let's say, 50 years ago. And a 100-year flood is a flood that's so bad it should only happen on average once every 100 years. It doesn't mean that if we had one last year, we can't have one again. And it doesn't mean that in 1,000 years we'll have 10 of them, but that's more likely to be close. And to say, oh, this flood's only supposed to happen every 100 years, which means that, you know, no one should see 2 of them unless you live over 100 years. That's also not true, right? But the idea is it's based on the probability of it occurring in any 1 year is 1 out of 100. That's all that means. And that's, of course, a theoretical probability that we're not 100% certain about. Find the probability of at least one 100-year flood in a 100-year period. The way it sounds is it's like who's buried in Grant's tomb, to which the answer is Grant, but it is not that, right? The probability of having a 100-year flood within a 100-year period is not 1. It's not guaranteed. If you wait 100 years, you'll get 1 and only 1 flood. No. Each year starts new with a 1 out of 100 chance of being a year in which it happens, but those years aren't spread evenly or anything like that. So the probability of having a flood in 1 year probability of a flood is 0.01. 1 year. The complement of a 1 year flood, right? Is 1 minus 0.01. So it's 99% chance you won't have a flood in any particular year. Just distributing them randomly. Probability of at least 1 flood in 100 years. So let's go with no floods over 100 years. Here it is, 0.99, if there's no floods. Do that for all 100 years. Now I left space here for a reason. If you wanted the probability of having no floods, you would only have that. But that's the opposite. That's the complement of what we want to have. Having none is the one thing we don't want to allow. So we're going to take the 100% as 1 and we're going to subtract that. We'll find the likelihood. Right? Complement is 1 minus what you don't want. This is 1 minus having no floods. So we'll make that count. And I can do it on this or even a less expensive calculator. As long as it has an exponent key, we're good, because you can go in and put the 1, I'll turn it on, 1 minus the 0.99 powered to 100, and then hit equals. Now this should definitely be a decimal between 0 and 1. Okay, if we knew there was going to be a 100-year flood, it would land right on the 1. I got approximately this. You can tell, looking at yours, about that. One more trace through. 100-year flood has this probability. No flood in a year has this probability. The probability of having 100 years in a row with no flood is this times itself 100 times, which makes up that. We want everything but that, so we go 1 minus, and we get that. So even though it's called a 100-year flood, if you look at a 100-year period, your expectation is about 63, 64% that it's going to happen in that period. And that's what we have. That launches you into homework 6, which is a nice mixture of problems from all the probability we've got. So I release it a little early for you to get to work on.